a break. You'll have a longer break during lunchtime. So it's my pleasure to introduce two young people who I've known for such a long time and been working with. And they're going to share their presentation about NIMMS and SEEIST. You've already heard Ugo mention it, Sandra mentioned it, and I mentioned it too. So, and you will really hear what they're doing. So Elena Benedetto is a coordinator of the SEEIST Medical Accelerator Facility Design. And after 10 years at CERN, she joined Terra Foundation. You will see lots of people join Terra Foundation as part of their careers, and to work on medical applications and to initiate the studies for SEEIST. And she's doing this in collaboration with CERN and the next iron medical machine study that Ugo alluded to, which is being coordinated by Maurizio Brettina and several European partners. And Mario Sapinski is an accelerator physicist who's an expert in beam instrumentation. He graduated from the Jagiellonian University of Krakow, and after his PhD work on the space experiment AMS, he switched to accelerator physics at CERN and then GSI, where he was responsible for the high energy beam lines. And finally, he's at PSI, but in between all of those going back and forth, he's been working also on SEEIST, together with Elena and Maurizio. So I welcome them both. So thank you very much. The floor is yours.
Thank you, Manjit, for the introduction and for inviting us to present our work. Indeed, Mariusz and I have been working several years on the design of the SEEIST facility, and together with the CERN initiative NIMMS. So we will discuss about that, and we will share this presentation. So at some point, I will give the floor to Mariusz and then back, and then. So let's see how it goes, this experimental way of presenting. So let's start to tell you what is SEEIST. SEEIST, okay, it's a very long acronym, stands for Southeast Europe International Institute for Sustainable Technology. It is a consortium of 10 countries to build a facility for cancer research and therapy in the Southeast Europe. Manjit showed the picture of Europe, where you clearly see that this region lacks of hadron therapy facilities. So our aim is to bring hadron therapy there, and an even biggest aim is to build a mini CERN. So to build a center where we develop scientific excellence and develop science for peace. So these countries will work together to achieve a high common goal. The SEEIST was initiated a few years ago. It's pretty young. It was initiated by Erwin Schopper, who was a former DG of CERN and had the experience of Sesame, again another project of science for peace, and Sanja Damjanovic, which is a physicist and was in the past Minister of Science of Montenegro. So thanks to her passion, I would say, she brought to the political bodies the proposal to build a therapy facility in their countries. Another important date is 2018, with the publication of the Yellow Book by Ugo Maldi and others. There were two facilities that were supposed to be, contending to see which one they wanted to build, either a light source similar to Sesame, or a cancer therapy facility that was proposed by Ugo Maldi. And finally, this second one was chosen to be further on. 1 year later, the studies for the accelerator design started at CERN. It was me and Mariusz, supported by European money within a team based at CERN and led by Maurizio Brettina. And finally, April 2021, so 1 year ago, we started HITR+. And finally now SEEIST can work together with many partners, many European partners within a big collaboration. You've heard from Manjit, this is not about only designing a facility, it's also about collaboration and sharing expertise in the medical, clinical, and radiobiology field. Studies continue within HITR+ and together with the CERN initiative. So let me talk about also what is CERN doing on this point. CERN launched the NIMMS study. NIMMS reminds the acronym PIMS that Ugo Amaldi discussed in the previous talk. So PIMS was the design who gave birth to CNAO and Meadowstone facility. NIMMS, 20 years later, will, let's see, crossing fingers, hopefully give birth to the new generation of medical accelerator. It is meant, NIMMS is meant to be really a toolbox, a toolkit. So it will not develop a facility, but it will develop a portfolio of technology leveraging on the CERN expertise. So we have work packages about Linux, synchrotron, gantry, magnets, artificial intelligence, and radioisotope production. It works as a collaboration. So we are open to discussion and to have joint seminars with several institutes. I apologize if I forgot some of you. Let me know so that the next presentation will be correct. And of course, we work together and supported by European programs. HITR+ is the main one, but we also have collaboration within IFAST. And we are connected with the medical and scientific community via ENLIGHT and the International Biophysics Collaboration. Now, SEEIST is really working at CERN, so our offices are at CERN, and we work together with the other participants to the NIMMS work. We share people, like our student is from CERN. Yeah, we work together, and that is really a perfect environment to do things. Okay, so what do we want to do for SEEIST? SEEIST will be a next generation facility, in the sense that we aim in having at least a factor 10 or 20 higher intensity compared to European facilities. Amaldi discussed about the challenges to achieve FLASH. This is indeed to address these challenges that we really aim in having a much larger intensity. And I will tell you why, how. SEEIST will do both research and therapy with different ions. So proton, helium, carbon ions, oxygen for therapy, and all sorts of ions up to argon for radiobiology and other kind of experiments. We take as a reference the carbons, and we aim at having up to 430 MeV per nucleon, which corresponds to a range in a water equivalent up to 33 centimeters. Okay, so it will have a flexible dose delivery modalities, and for that we need a larger intensity. And the baseline is a PIMS-like synchrotron. So the one developed at CERN 20 years ago that gave birth to CNAO and Meadowstone. Plus, we have also the option of having a compact superconducting magnet synchrotrons that will push the boundaries of the hadron therapy, I mean of carbon therapy indeed. As you see from this table, these are the parameters. So energy for carbon ions up to 430 MeV per nucleon. For protons, okay, 250 for treatment, but of course, higher energy will be also available for radiography with protons, in example. And okay, these are the specification of PIMS design. You see an intensity which is a factor 10, 20 higher than what is done today in the European facility. And in particular for carbon ions, we aim at 2 10 to the 10 ions. This is what is required to deliver the full 2 gray dose to a 1 liter tumor within 1 synchrotron cycle. Okay, so in this talk, we will guide you to the components of the SEEIST facility, and therefore we will discuss these layouts that you see both in the rendering and in the map. So Mariusz will give an introduction about accelerator, then we'll discuss about the source. We have three sources, the LINAC, here as well, sources and LINAC. Then I will discuss about the synchrotron and the challenges associated to them, talk about the gantry that we plan to have here. And Mariusz again will talk about the design of the high energy beam lines, and in general, the philosophy that we choose for the layout for the facility. This facility, again, is both to do treatment and clinical. And as you can see, we decided to really separate the two environments. So here we will have the treatment rooms. Here we will have the experimental hall. So this is our goal. And I give now the floor to Mariusz to continue on this presentation.
Yeah, good morning, everybody. Before I start, I want to add something to my biography. I was also in Terra for some time. So Terra is really a good foundation that hosts a lot of people at some moment of the career. Now, I like to start with this slide, which is maybe a little bit trivial for accelerator people, but not all of the students are familiar with accelerators. So all the accelerators, or almost all accelerators that we are used right now, are based on radio frequency. And the question, of course, rises why. It's a very fundamental question. Well, if we start thinking about the four fundamental forces that we know exist in nature, so the gravity, electromagnetism, and the nuclear forces, then we find very fast that gravity is really weak, even if that's not what you think when you fall on the floor during the sport, but actually, if you think about accelerating ions by throwing them from let's say, Tower of Pisa, then after 57 meters of a free fall, they only gain some micro electronvolt of energy, which, you know, a usual 1.5 volt battery gives much more energy to a proton than falling from a 57 meter tall tower. So we have to exclude gravity. Nuclear forces, so there are two in principle nuclear forces, strong force and weak force. Well, altogether they have a range way too small to be used to construct something microscopical. They actually have a range of the size of the ion or proton. Therefore, we have to exclude them. What remains is electromagnetism. And electromagnetism is actually one force, but we like to describe it as a combination of electric field and magnetic field. It's because it's actually, it's a way we describe it. We like to think about it. There are some people who are really geniuses, and they manage to think about it as a one vector or tensor with four components. But let's say at this level, we describe electromagnetism as a combination of electric and magnetic field, and electric field acts let's put it like that. Magnetic field always acts perpendicular to the direction of the motion of the particle. So in principle, there is no energy gain, because every time you want to kick, you actually turn the particles, which means that it's also a very useful field to control the beam where it moves. However, it's absolutely not useful to accelerate particles. Therefore, what remains is the electric field. And the last choice we have to make is whether we use a static or oscillating electric field. Static field allows for one-step acceleration. So let's say we have 1 million volt potential difference, and our particles can get 1 mega electronvolt energy in case of protons of electrons or electrons. That's it. It's very difficult to get electrostatic potential higher than 1 megavolt. Where I see here nearby, there is a system which actually reaches 860 kilovolts. And it's already a very big installation. Therefore, it's better to use oscillating field, which allows to give kicks to the particles continuously and allows to reach much higher energies than this 1 megaelectronvolt limitation. That's why, so oscillating, it's good. Oscillating electromagnetic field is basically radio frequency field, and that's why we use radio frequency field for particle acceleration. All right, so next slide, thank you. So what is this structure that is used to accelerate particle, which confines the electromagnetic field and which creates right conditions to acceleration? Well, this structure is called accelerating cavity, and there are really many types of accelerating cavities. It's usually made of metal or superconductor. If it's metal, then we like to make it out of copper because copper has a very good conductivity. And the whole science is in the shape of this accelerating cavity. The shape of the cavity should be such that in the place where the beam is accelerated, the electric field vector oscillates in the beam direction. All right, and you see it on this plot here. You have magnetic field lines which are blue and electric field lines which are green, and they oscillate in the opposite directions, right? Once they go to the left, once they go to the right. Therefore, when the beam is injected, it has to be injected in the right phase, so it's actually accelerated and not slowed down. And we feed this cavity with RF field, which is generated by like in the by a device very similar to something that exists in microwaves, for instance, the microwave ovens, but of course with much higher power. So sometimes we call the cavity a resonator. And this is because it usually operates at a very narrow resonating frequency. And why this is important? Well, it is important because if it's not a resonator, then it's an antenna, and most of the energy you put in is actually radiated away. So you have to confine it in something which has a resonating frequency the same as the RF frequency, and the field, the losses of the energy are much smaller than if it's not the case. Some cavities, like for instance the cavities which we are using in synchrotrons for radiotherapy, they can be tuned in the very wide range of frequency. And our cavity, for instance, it's tuned in this range between 0.5 and 3.2 megahertz. Now, so this frequency at which the cavity works is important. It's usually very well defined. Usually, or I mean, if the frequency is higher, then the elements are smaller. Yeah? So for instance, you will see soon on next slides shapes of accelerating devices for different frequencies. And injector Linux that exist, that are employed in European facilities and in Shanghai, because Shanghai facility is the same as Marburg facility, they use the frequency of 216 megahertz. So I mentioned it because like that you get familiar with typical frequencies that we are talking about. This injector Linux, they reach maximum accelerating gradient of around 18 megavolt per meter. So now you compare it maybe to this free fall of a proton in a gravitational field. It's orders of magnitude smaller. And the average field, because of course you cannot, it's oscillating field. So you accelerate particles, but not all the time. You have to have spaces where they drift. The average is 5 megavolt per meter. As I said, higher frequencies are smaller dimensions and usually higher accelerating gradients. And for instance, the king of the acceleration with RF fields are structures that were constructed for click accelerator, which can reach 100 megavolt per meter at 12 gigahertz RF fields. Now on Friday, I think you will have some you will have a presentation about a light system where 3 gigahertz field is used to accelerate protons. All right, next slide. Yeah, Elena tells me that I can take control, but maybe it's a bit too complicated right now. If you don't mind, I will continue like that.
Sure.
Thanks. Okay, so we have this cavity, which is the heart of accelerator. And then we have really, I mean, all possible layouts of how the cavity can be installed and what are the acceleration scheme. Let's start with the two which are kind of opposite. One is a LINAC, which you see on the first plot, which is basically made of accelerating cavities or accelerating gaps. We call it also sometimes gaps, just to confuse you even more. So it's very simple. There is a cavity after cavity, and of course, because the speed of the particle is higher and higher, then the distance between the cavities, or the way the cavities are made also changes. Opposite to that is a synchrotron, where there is only one cavity, and the beam comes back to this cavity and is guided all around using magnets. So in the LINAC, basically, the most important part is the cavity, and it still usually employs magnets to control the beam, but what is important is the highest possible accelerating gradient. While in the synchrotron, cavity can have some tens of volts of accelerating potential, because the beam will come back millions of times, and this tens of volts will be multiplied by millions, and you will get high energies. While the magnets became very important in synchrotron. Now we already heard in Professor Amaldi's presentation about cyclotrons, which basically a cyclotron is shown on this plot below, and yeah, thanks. And basically, what is happening here? You have one big magnet, and the particles are accelerated in the gap between the two halves of the two electrodes, basically. Where the polarization of the electrodes change. It's usually also driven by the RF field, and it moves in a spiral. Yeah. So this is the cyclotron, and they are, of course, very widely used in particle therapy, especially for protons, mainly because they are very simple. You don't have, you just have an ion source. Very simple is maybe exaggeration, but they are simple. You have just the proton source in the middle, and the protons, they drift out of the source, and immediately they meet the accelerating gap, and they are accelerated to higher and higher energies. The problem here is that, yeah, first of all, you start having, if you want to go to very high energies, your vacuum chamber, which has a shape of this kind of disk, or yeah, starts to be very, very big. And this is very difficult to be produced. And usually when higher energies are to be reached by cyclotrons, then there is 2 or 3 stage acceleration. So there are 2 cyclotrons separate, which work, yeah, which are constructed in different way. Then there are other types of accelerators, like, for instance, fixed field alternating gradient machines, or synchronous cyclotrons. Or synchronous cyclotrons are actually used in therapy, but FFAs or fast cycling synchrotrons, they are not yet used in therapy. There are plans to do this, but these machines are kind of still more researched than used for this kind of applications. And FFAs are very interesting machines. I don't know if we will have anything about them later, but basically they are generalization of cyclotron and synchrotron. So there are machines in between They have advantages of both, but yeah, for the moment at least, they are not applied to particle therapy. And then there are, of course, non-radio frequency accelerators, electrostatic accelerators, dielectric accelerators, plasma accelerators. Electrostatic is something that is not used because we have this 1 megavolt limit. The electric and plasma accelerations, these are new developments, and I think we will have something about that in the afternoon. All right, next slide. So here is the first choice we had to do when we started to work on SEEIST or NIMMS. What is the base? What configuration should be chosen for the new therapy facility? Because up to now all the carbon machines are based on synchrotron, and we were thinking whether this is we should turn into something different. Because we are not the only ones. There are collaborations even within CERN. There are some works on linear accelerator for carbon therapy. There are also other projects where FFAs are proposed. And the question was, what shall we think about? And after a lot of considerations, we decided to stay with synchrotron. The reasons for that, there were several. One is that it's actually quite good and well established. And at some point, we thought that SEEIST may be constructed rather soon. So there is not really so much time for development. But also, synchrotrons are easy to configure. So for instance, when you have a cyclotron and you design it for carbon, then it's not so easy to switch it to protons. It's possible, but it's not an easy operation, at least now. While synchrotron can have one cycle, which is carbon, the other cycle, which is protons, even different types of ions like helium-3, which has different charge to mass ratio than protons and carbon, could also be easily accelerated in the next cycle. So this flexibility is very important. Then the next is change of the output energy. In synchrotron, it's very easy to extract beam at lower energy. In cyclotron, which is the biggest competitor, it's basically almost impossible. It's again, there are variable energy cyclotrons, but they are not used for therapy. They are complicated machines, and change of energy takes rather hours than seconds. Therefore, in the medical cyclotrons, the energy is regulated by basically by putting in the beam a material which is slowing down protons. It works well. However, for instance, if you want to get 60 MeV protons, for instance, for eye treatment, from the machine which gives you output energy of 250 MeV, then what you get on the patients, it's less than 1% of the initial beam intensity. All right, so it's very, very inefficient, and all the rest of the beam is lost somewhere. It generates a lot of radiation. So this is in principle one of the biggest problems of cyclotrons, and that's also why we decided not to go with cyclotrons. Right, and all the existing carbon therapy facilities right now, they are based on synchrotrons. Of course, there are disadvantages, and they were already partly discussed. It's difficult to get enough intensity to perform flash therapy, but we still think that we should be able to do it. All right, and the next slide. All right, so the acceleration starts, or the beam starts with ion source. There are many types of ion sources, but for ion therapy, usually we use commercial electron synchrotron resonance sources. They are chosen because of they provide quite high beam intensity. The emittance is not great, but is acceptable. But maybe the other very important for medical facility aspects are reliability and operational simplicity. So they can work for months constantly, providing the beam. There is a minimum service required. How do they work? Basically, they are big ovens with again fed by the microwave, where you inject some kind of gas, and changing the gas, you change the beam you obtain. So from the same source, you can get protons, carbon, helium, which is very nice. And you have the plasma is confined in magnetic field, and this magnetic field only allows particles of a certain charge state to go out. Of course, this is a theory. In reality, there is a certain spectra, and there is a certain pollution in the beam that is coming out of the ECR source, but we are dealing with that. And here you see, basically you see the two plots. One is showing how it works, and the other one is showing a little bit the configuration of the magnetic field, which is quite complex, which contains two solenoid magnets at the ends and multiple magnet in the middle, usually octupole magnet, which altogether produce a field which confines the plasma. All right, the next slide. For the ion sources, so currently European centers use usually Pantechnic super nanogun sources, which provide carbon current of 200 to 250 microamps. In Japan, they are a little bit better. They use, but it's very difficult to get information from Japan. They sources are usually provide a little bit higher current. They usually work with slightly different intensity. It's actually, you know, I say K series, and there are so many types of K that this parameters mentioned here are not always true. Nevertheless, I think the message here is that the current existing commercial sources can provide enough intensity for protons and for helium. However, we have a problem with carbon, because if you want to inject this large intensity of carbon into the machine, what Elena was showing, then we actually need a source which provides around 600 microamps. And there are sources like that. They are more still in R&D phase, but basically the direction in which it goes is that the RF frequency, so the frequency at which we are powering the source, is usually increased to 18 gigahertz, and they are using superconducting magnets, but without helium, so based on cryocoolers. An example of such a source is Aisha source, which actually should start operation in CNAO this year, and probably they maybe correct me later, maybe it's already operating. And similar sources are being operational in Japan, or even Pantechnic is working on a source like that. So actually, our requirements in terms of ion sources are rather covered for NIMS. Here you have a picture of a super nanogun source, which is the one which is widely used in current centers, and you don't see the scale, but it's pretty compact. It's really not a big source. It weighs several hundred kilos, but it's really not a big object. All right, the next slide. What usually is rarely discussed is the ion source extraction system. The ions are produced with rather low energy. So the plasma, when they're drifting out of the plasma, they have some single electronvolt energy. So the first thing that is done is the extraction system, which is little electrostatic accelerator, which allows for them to reach, let's say, 8 kiloelectronvolt per mass unit. This is the current value, and for NIMS, we would like to increase it to 15 kiloelectronvolt per mass unit, and we want to increase it because if we do it, then we have less problems with the space charge. Space charge, it's also something we don't really discuss here, but it leads to blowing of the beam, which is not good, because then we want to have very small beam for the injection of the synchrotron. All right, maybe in the next slide. Yeah, here we have here the message is that we have several sources. We foresee in NIMS 3 sources, the same as here for Med-Austron. And the reason is that, of course, we want to have a spare source if something goes wrong, and we have to treat patients all the time. But also, you know, that they are in principle interchangeable, so you can change the gas you put in and you get another beam. But we would like to, it takes a quite significant amount of time because you have to purify it. Therefore, it's good to have a dedicated source for protons, for helium, and for carbon. All right, so after the sources, the next slide, we have injector LINAC. Injector LINAC brings the beam from this energy of 8 or 15 kiloelectronvolt per unit to the injection energy of synchrotron, which is somewhere between 4 and 10 MeV per unit. And basically, all injector LINACs nowadays are made out of two sections. One is radio frequency quadrupole, and the second one is drift tube LINAC. And here I come back maybe just a point about cyclotrons. They do not require this injector LINAC, which is very good because yeah, they are much simpler. Here you see, maybe before we go to the next slide, on the left plot, you see the shape of the electrodes of the radio frequency quadrupole. And you have to imagine that this modulation of the shape of the electrode, it must be done with micrometer precision. And on the next slide, you will see that thanks to this, yes, please, next slide. Thanks to this, this modulation, we achieve very interesting things with the RFQ. First of all, you know, the beam which is coming from the source is continuous, and we achieve bunching. So we divide the beam, we focus the beam longitudinally into bunches. Then we actually also focus the beam transversely because we have 4 electrodes, and altogether they work like a quadrupole, and the quadrupole magnet is focusing the beam. And last but not least, we actually accelerate the beam from this very low energy to around 400 kV to up to 5 MeV, depending on the concept, which allows us afterwards to inject it to the next acceleration stage, which is drift tube LINAC. Unfortunately, RFQ is not very efficient in acceleration. Therefore, we tend rather to end RFQ as soon as there are not any more problems with space charge. So for instance, in the current machines, the RFQ finishes at 400 kV per nucleon. For NIMMS, we think rather around 2 MeV. On the right plot, you see 2 RFQs. One is the upper one is the current RFQ, which is used in the machines in Europe. It operates with 216.8 megahertz, and it's so-called 4-rod RFQ. So you see that it's 4 rods, and they have, you don't see it from this picture, but they have this modulation of the electrodes. Below you have a very interesting new development. It's actually a picture from the last IPAC. It's a 3D printed 750 megahertz RFQ, which is something that is also developed in collaboration with CERN and Riga University. From here, I would like you to just pay attention to the sizes, to the scale. Maybe you see that the 750 megahertz machine RFQ has much smaller dimensions. Yeah, the beam has to fit into much smaller space than 260 megahertz RFQ. And this is what I was saying, with the increase of the frequency, you have to go to smaller structures, which is good and bad. I mean, it's good because smaller structure, yeah, is more compact, is also more efficient usually in acceleration. However, it's more difficult to cool and more difficult to fit a beam which may be actually large. Therefore, actually, I will maybe skip these 2 points and go to our NIMMS choice. We are still working, come back. We are still working on 3 possibilities for the RFQ. We are working on 352 megahertz RFQ with this final energy of 2 to 3 mega electron volt per unit, but with very high duty factor. It's based on LINAC 4 technology. We are working on this 750 megahertz RFQ that you have on the right, and we would like to explore possibility of 3D printing of such a device. But we are still looking into original 217 megahertz RFQ, redesigned for higher duty factor, mainly because the bigger structure is easier to cool down. All right, next slide. Here you see the whole injector. So there is a RFQ on the right. You don't see it very well from the photo, but it's seen on the diagram. And then there is this pink tank, which is the drift tube LINAC. It's actually made by a company which is called Pink in Germany, and it contains this drift tube LINAC. Here you also see, this is the picture and the drawing from CNAO, and you see 2 ion sources. Nowadays, CNAO is also putting the third one. Right, and there are a lot of other things here, which I am not discussing, but there are magnets, there are choppers, all these things that they could be discussed at some other point. Okay, next slide. So injector LINAC is a drift tube LINAC. Is much more efficient accelerator than radio frequency quadrupole. The legacy LINAC is this 260.8 megahertz LINAC, which accelerates, and this is important, carbon 4+. It's not 6+, it's 4+. There are several reasons for that, but the main reason is that this is the ion we get abundant from the ion source. It's very difficult to get a lot of 6+. Of course, we would like to have in the synchrotron 6+, because there is no point to have lower charge to mass ratio. It's just less efficient to accelerate. You need bigger synchrotron. So we do the stripping, so removing of the last 2 electrons after the LINAC. Japanese, they actually have a very similar structure. Sometimes they have lower injection energy, but they operate also very often at this 200 megahertz. And for NIMS, we actually go into something quite complicated. Instead of 1 tank, we would like to have 3 tanks. And why is that? First of all, because there are 3 applications. One is injection of carbon ions, and for that we can go down to 5 MeV per nucleon. In the second tank, we would like to accelerate protons to higher energy. That is because the space charge effects are important for protons, and it's better to inject higher energy protons to the synchrotron. And the third tank is actually inverse, I think. But anyway, the second and the third tank is actually for protons and for radioisotope production. All right, we would like to use this LINAC not only to feed the synchrotron, but also to generate high intensity beam, hit a target and produce radioisotopes for medical purposes. And I think the biggest challenge here, except of complication due to these 3 tanks, is that the maximum duty cycle we increase from current less than 1% to around 10%. And what it means is that much more heat is generated in the structure, and this heat has to be evacuated. We think that 10% duty cycle, we are still safe, and we can cool down the machine. All right, so the next slide. The next slide is actually Elena. So sorry, I took a long time.
Okay, so this is on me now. So now we can inject in the synchrotron, and for that, in addition to the electric field, we also want to exploit the magnetic field. So what are the key components of a synchrotron? This is a very old pictures for LEP. So, but the point is that we need 3 main components. The RF cavities that you have seen before with Mario, they are the element that accelerate the beam. Then we have in a synchrotron, we need bending dipoles. These are the magnets that bend the beam. So this is the formula. So you play with your you know, the rule of the hand, and then you see that if you multiply the velocity time the bending field, and the bending field, let's imagine it's coming in the vertical plane, so you end up with a force which direct the beam toward on a curved trajectory. So thanks to bending bending dipoles, you can actually curve the trajectory of the beam. Bending dipoles, we have really different types, from the normal conducting one, so like this one, up to the LHC superconducting dipoles. Then we have a third element, which is important, and these are the focusing magnets, the quadrupoles. Instead of having only one field which is perpendicular to the plane of the direction, this element is obtained with 4 poles, and I will show you a picture of a real one. So you have 4 poles that generate a field, a magnetic field, which goes from the south to the north, or vice versa, I never remember. And if you do so, and again, you do the exercise with your hand to see where the force is directed, you see that in one direction, the force is directed toward the center. So in one plane is focusing. In the other plane, it is defocusing. The big things about quadrupoles is indeed that they focus in one plane and defocus in the others. So in order to focalize your beam and avoid that it gets too large, we need to have an alternating structure of magnets which are focusing in the horizontal plane, and this is represented by this lens, and then defocusing in the horizontal but focusing in the vertical, and vice versa. And if we do so, the beam is following not a straight line, but it's kind of a pulsing, so periodically oscillating between maximum and minimum. So these are the key elements of a synchrotron. And now let's recap a bit of beam dynamics. So just a few slides about what we need. The first concept that we need is the rigidity. So how difficult, related to the dipole, so how difficult it is to bend a beam. This is the same formula as before, but then you equalize with the centrifugal force and you end up with this that tells you that B rho, magnetic field times the bending radius, is proportional to the momentum of the particles. This means that the higher the energy of the beam, so the beam momentum, the higher the bending field you must apply, or the larger the machine should be. Typical numbers are, magnetic field for normal conducting magnets, you have up to 1.5 Tesla. And if you go to superconducting technology, you can go to 3 Tesla or even more. And therefore, for a given energy of the beam, you can reduce the radius of curvature and therefore the dimension of your machine. So now here you see what is the beam rigidity of the particles that you need to do radiotherapy. Electrons for conventional X-ray machines have a very, very small rigidity. Now you go to protons and it's 2.4 Tesla meters. And now you go to carbon ions and it's a factor 3 higher. So thanks to this formula, it's easy to have a feeling of why carbon ions machines are 3 times larger than proton machine, or 3 times more difficult, or whatever you want to put it, or we need to do magnets which are 3 times more powerful. So what is the beam doing? What are the particles doing in the machines? So let's imagine that this is the circumference of your beam. Now, what happens really is that particles and the entire beam do not follow this ideal trajectory, but they oscillate slowly around the circumference, okay? And the number of oscillations that the particle is doing per turn is a very important number, which is called the tune of your accelerator. We normally, last point, we normally describe the motion of the particles in a synchrotron in a 6D phase space, or portion of it. So in principle, we are interested both at the position of the particles, but also at its divergence. Divergence is related to the velocity and the direction of the velocity, and it's an angle. Okay, so in this plane, the phase space, here I show you the horizontal phase space, so X and X prime, so the divergence in the horizontal plane. The beam is moving according to this formula, the Hill's equation. You see, it's similar to it's very similar to an harmonic oscillators, but this coefficient here is varying. And this is varying according to the arrangement of quadruples that you have in the machine. And if you solve this question, you have these solutions, and you realize that while the beam is going to the accelerator, the position vary along an ellipse. Okay, if it was an harmonic oscillator, it would be a circle. Here as well, we have the possibility to transform it into a circle graph. Key message is particle in an accelerator and in a beam moves along an ellipse that we call it accelerator ellipse. Now, what's happening to the whole ensemble of particles? They also stay in an ellipse. Okay, so if at a given point you have a look at what all the particles do, they again in the phase space plot. So this is not the real space. This is X and the velocity. All the particles again occupy an ellipse. And while the beam is evolving along the circumference, the beam is evolving according to this ellipse that changes shape according to what we call beta function. And an important point is that the beam envelope, so the beam size along the accelerator, is proportional to the square root of the beam function. So now, this is the C synchrotron, the baseline. This is based on a PIMS design. And here, in example, you see the beta functions for this accelerator. So if you do the square root of these two lines, you access the envelope of the particles while they travel along the entire ring. Okay. This is the conventional, I mean, the PIMS design. So the lattice based on, I mean, the design done 20 years ago at CERN that gave birth to KNAU. Okay, in this figure, you see the dipoles, the blue elements, and then you have quadruples in between and other, all the other elements. And here you see it as well in the sketch. So the dipoles are this big block here. And in between, you see that there are these F and D elements. And these are indeed the focusing and the focusing quadruples that we need to confine our beam and to give such a kind of periodic function that you have for the beam size. Okay, so this lattice, we keep it as a baseline for our SEEIST synchrotron. The final design will not be exactly the same because we want to go to much higher intensity, so a factor of 20, and flexible delivery. So at some point we will do modifications to the injection and extraction and probably also to the lattice. But let's keep this as a starting point. As an option, we have developed a superconducting magnets compact ring for carbon ions. Actually, this was done already in the past when I was at Terra, so after an idea of Ugo Amaldi. And this is a very compact ring, 30 meters circumference, and it is based on 90-degree magnets, superconducting magnets, with a field of 3.5 Tesla. You see here how this small compact superconducting ring with this gantry compares to the PIMS machines. So this is a KNAU realization and this is Medostrom. And as the professor was already saying in the previous talk, at KNAU, they already made a big effort to be as compact as possible. So you see that the LINAC was put inside the synchrotron to save space. This is the synchrotron, which is large. And then also the lines has been designed for compactness. Med-Ostrom, okay, it's large because they believe it was better to keep a space available for different options. But you see the clear reduction of dimension if superconducting technology is applied. Now, within HITR+ and within NIMMS, we decided to go for a different lattice based on 60-degree magnets. Again, superconducting of the same kind of before, but we believe that 60 degrees are less complicated, still a challenge, but less complicated to wind compared to a full 90-degree structure. And then there is a quadruple in between to achieve good focusing. We based our design on alternating gradient candid cosine theta magnets, because they give the possibility to have, in addition to dipoles, also nested quadruple components. So to continue focus and defocus the beam, even inside the bending magnet itself. This is the advantage that the beta function gets smaller, and therefore also the beam size and the dimension of the magnets. Now, this triangular ring, just to mention one of the things that we are also developing at CERN, we decided also to develop a small machine based on Ward magnets, similar size as the superconducting one, but for helium ions only. Heliums are lighter than protons. They have several advantages that I'm sure that will be covered later in the week. So we are carrying together the development of this machine based on Ward magnets and this machine based on superconducting magnets. One is for carbon ions, the other is for helium ions. Where we have the synergies is in the definition of what is the equipment in the straight section. This is a very compact machine. The main challenge, okay, it's the optics, of course, it's the injection, extraction, the magnets. But what is also important is the space. So what is the equipment that you can afford to put in this space? And for what do you need to find solution to minimize the space? So we really make an effort. This is not only a nice drawing, this is done together with the mechanical team at CERN, where we really try to put real hardware components inside this layout to see whether they really fit. This is really an issue of space. So based on that, we will feed back into the optics, both for this ring and for the superconducting ring. Magnets will be superconducting, and for this you will have a lecture later on by Lucio Rossi, which is the expert on that. Here, let me show you two magnets that we are looking at. The one is the prototype developed at Berkeley, together with the collaboration with PSI and Varian in the past. This prototype was to build a gantry with a very large acceptance and therefore aperture. You see the aperture of this magnet, it's huge. It's 400 millimeters, so 40 centimeters aperture. This was tested successfully up to a given field, pretty high, but then, okay, they had some issue, fine. Now, the second magnet that I would like to show you is the one that is being developed for the high luminosity LHC. This is, again, a candid cosine theta magnet. So you see candid means tilted. And here you see that these two layers look like solenoids, but they are tilted. And the two together produce a pure dipole field in this case. And here you see the dimension of this magnet are 2 meters long, and the beam, the aperture is 100 millimeters only. This is more or less what we want also to have. A bit of complication. Imagine to take this magnet here and to bend it by 70 or 90 degrees, and you have our magnets that we want to have in this compact ring. So pretty big challenge for the manufacturing. Lucio will show you that we have several prototypes that will be built within 3 to 4 years from now to really test the feasibility of these windings and this curvature. And then I would also like to mention a work that we are doing, because if you have such a strong curved magnets, we don't know how to deal with it. I mean, this has never been done before. Codes, our simulations codes are not made for that. Our simulation codes deal with LHC kind of magnets, which are straight. We want to have it really, really heavily curved. So the bending radius is 2 meters. It means that this guy is 2 meters long and needs to be bended by 90 degrees, resulting of 2 meters bend. They are comparable, this I mentioned. So we are working on that within a work package combining beam dynamics, which is myself and Dani Barna, which is magnet measurements. And we are agreeing on basic formalisms, and as well how to treat the field that is rising at the edges of the magnets. Okay, now another point. For our machine, we need flexible beam delivery, and this requires having a very high intensity, a factor 10. And now I tell you why. Because as of today, machines in Europe, for every energy that is needed to do the painting, they have a different cycle. So you see here a sketch. This is a typical accelerator cycle. So you inject the beam, then you accelerate, and then you have a flat top where you extract your beam at a given energy. And then you have what we call washing of the magnets, so that you have to do a gymnastic. You bring them to a higher field and then back to the energy injection point. And then you proceed to the next cycle. And then you accelerate to a different energy. You extract, again, washing and deceleration, and so on and so forth. In this period here, which is 1 to 2 seconds, the beam is not extracted. This is wasted time. So we want to get rid of it. And how to do it? Okay, this is what the Japanese people do. The Japanese machines, especially iMac, they decided to they successfully implemented the acceleration up to a top energy, and then a deceleration in steps. And every time that you decelerate, you can extract beam at different energies. Therefore, you save all this wasted time. The point is, you need to have already stored in your machine all the intensity that is needed to paint all the energy. So you need at least a factor 20 to do the entire beam in one shot. Another development, flash. And flash requires high intensity in a shorter time. And even for this, indeed, it is needed that we go to much higher intensity compared to what is done today. Now, how do we do that? With multi-energy injection. So this is our goal, 2 × 10⁻⁻⁻ carbon ions. You have seen from Mariusz that conventional sources are about 200 microamps, but new generation might go up to 600 microamps. So here we have gained a factor 3, but still we have the challenge to inject a factor 20, not a factor 3 that you gain with the source. So for that, we need a much more advanced multi-toy injection scheme. This is again a plot in the phase space, so x prime. This is the full size in the phase space of your beam. And this one small red part, this is the size of the beam coming from the linac. So it is much smaller than the size of your beam in the synchrotron. And the idea is to inject multi-turn so that you can completely fill the phase space. Now, these are studies done in the past by Amila Advic from University of Sarajevo. which is part of the SEEIST studies. So she came to do an internship with us and compiled her master thesis on that. You can change the shape of this injected beam anywhere, I mean, as much as you can. But the final point is that whatever the configuration, you still need at least 13 effective turns injected in the machine. Now, if you think that the efficiency of this process is 60%, means that you need to inject for 26 turns, which is a lot. If you would go for a compact machine, you would need a factor 2 higher, which is not feasible at all. So we are considering different injection schemes, like this very complicated one that was done at CERN for Lear, or I mean, how to deal with that. This is what we currently stand. Concerning extraction, so again, these are plots from Rebecca Taylor, so our student from CERN. I show you that the phase space, normally it's an ellipse, but now it is a triangular. This is a triangular because we have used other magnets, which are called sextuple. So before we were talking about quadruples, now sextuples, to excite some non-linearities. And then bringing the tune close to a third order resonance, which is excited by the sextuple, we managed to deform the phase space. So instead of an ellipse, we have now a triangular. And if you insist in this exercise and you move closer and closer to the tune, you end up with a very unstable configuration. I want to show you the beginning and now the formation of the triangular. And now you see that there are particles which are not staying any longer in the phase space, but they are spilling out. And if you manage to catch them and bring them nicely out of your machine, you manage to have a spill, a continuous spill of particles that allows you to do dose delivery in a slow way. This is another study done by Rebecca. And these are preliminary studies that she did to see whether it was feasible to accelerate a bit this slow extraction to reach flash conditions. And okay, our consideration so far is that you would need a much higher voltage for the RF knockout, and this is a bit beyond our capability. So we need to invent other ways, and we have ideas on that. Okay, carbon ion gantries. Here, let me see. Oops. Okay, so here the message is, depending on the beam rigidity, carbon ions gantry have different size and complications. And here you see an X-ray equipment, what you find normally, because this is provided by electrons. This is a proton gantry. And this is on the same scale, the carbon ion gantry of HIT. So pretty huge and 600 tons. In Japan, they have developed the first and only superconducting gantry. Here it is, installed and working nicely in Haimak. And now they have just installed a new one with a higher magnetic field in Yamagata. And we also have development in this sense. Started within Terra in the past, and now continuing within HITR+. And there will be a talk by Marco Puglia on that later in the week. Okay, so I'm giving back the floor to Mariusz for the last part, the layout and the beam lines.
And just to say 5 minutes, please.
Oh, okay, that may be a little bit challenging. Yeah. Okay, I try to squeeze it. The high energy beam transfer lines, these are the lines which, if you look, they start at the extraction of the synchrotron and they bring a beam to the patient. I don't know if you see my cursor. I hope yes. So all this zone, it's quite big zone, is called high energy beam transfer lines. They're called transfer lines, but of course it's not just simply transferring the beam. it's also forming the beam to such a shape that it fits requirements. And I will talk about it a little bit later. Now, what is important here is that in principle, the way you design transfer lines depends really a lot about on your space that you have available. And we already said, was already said today that Heidelberg and Knau, for instance, they had rather small available space. Therefore, they went to very particular solutions where, for instance, here there is a 90-degree bend, 2 times 45 degrees, and the rooms are very small and they are very close to the machine. And in case of Knau, it's even different. Yeah, there is this three-way splitting magnet and right, and the vertical line. If you go to, it says I can control it, but I cannot control it. Elena, can you change the slide? Oh, no, wait. Okay, I think I can. The facilities in Austria and in Marburg, they were designed with much more space in mind. Basically, the transfer lines they occupy 30–40% more surface, and here you see how they look like. So there is a really vast space, no big considerations about compactness. Now, what is important, because I have not so much time, so I skip this slide and I go directly to this slide, is that the way the slow extraction is done, so what Elena was talking about, produces very particular beam, and this is really crucial for us. This beam, you can see it here. In the plane of the extraction, so in the horizontal plane, the beam has actually shape of so we call it bar of charge. So this is the ellipse we were talking about before, the beam ellipse, but actually it's not really filled by the beam. Beam travels only in this very narrow area of the beam ellipse. And therefore, there are basically several ways or different ways to control the beam size on the patient. One is, so typically the beam looks like that, and the beam size on the patient is controlled by basically the size, by the beta function, we call it. In this case, we can control it by the beta function, but we can also rotate just the bar of charge inside the beam ellipse. And that it's quite complex to explain, but that brings some complication, but also some advantages to the way the transfer line is designed and is set up. We can talk about it maybe later. Now I will just would like to say two more things. There's this beam size which is defined by the beta function, but there is also a property of the beam line which is called dispersion. Dispersion is basically what you know in the dipole magnet. When you inject beams with two different energies, they travel with different paths. We don't want this on the patient. We don't want this on the patient because that leads to the increase. I mean, the beam is never monoenergetic. There is always some spread of the energy, and we don't want this spread to appear as a bigger spot on the patient. Therefore, we have to construct the beam line such that it's dispersionless. It's quite important consideration, and it's treated differently in different facilities, but it's important. Finally, the beam divergence is very important. So here you see the patient and the beam coming to the, let's say this is the tumor, coming and is very divergent. We don't like this situation because in this situation, if we make small error in the position of the patient from the end of the beam line, then we will get very different beam spot, right? So we want the beam to be parallel. We say, yeah, not divergent. Yeah. So this, as you see, all these features, they have to be taken care by the magnets in high energy beam transfer lines. So it's not only just simple transferring the beam. So here is our concept. Here is the synchrotron. Then we have something which is called dispersion suppressor. There is this main or principal beam line, and there are the branches going to here to the treatment area, and the other branches going down here to the experimental area. All right, this is considered, I mean, developed considering greenfield approach, so we don't have space restrictions. We would like to have very large irradiation rooms to host a lot of equipment. We would like to have also very large experimental area so that, you know, I mean, there are no problems with, for instance, irradiating big animals. And we want to have this separation that we already talked about, that the treatment area, experimental area is well separated, because the patient who goes to be treated doesn't want to see big animals coming on the other side. And the last thing is that the design should be expandable, flexible. We can create next rooms here. Yeah. Or we can convert those beam lines to gantries. I probably don't have much time.
You don't.
Then I will.
No, because some really interesting things, and I want the
Yeah.
students to be able to ask you questions.
All right, then I will skip this, but I will say a few words about the beam chopper. Beam chopper is a device which is usually right after extraction from the synchrotron, and it's made of a chicane. So you have a beam coming, and beam is always reflected and travels around the block of a beam dump. So these four magnets are connected together, and if we don't power them, then the beam is switched off, okay? It's a very important safety feature. If there is a problem with irradiation to the patient, you switch off the beam very fast by making it hit this dump block. This currently, it allows, I mean, the current solutions, this switching off of the beam takes around 200 microseconds, so it's quite fast. However, for the flash therapy, we would like probably to go faster. And one of the ideas is to make this chicane on the two sides, so to have two dump blocks. And when you switch off this time 6 magnets, then the beam is cut at the same time from two sides. Therefore, the abort time is roughly cut by 2, so 100 microseconds. All right, so there is this beam chopper, which is important. Then I think this will be, somebody will talk about it later, so I will also skip that. And I think, all right, just this plot here on the right, this is a typical setting of the beam line. Here you see the end of the synchrotron. So the septa of the synchrotron, these are still synchrotron magnets. Then we have this part, which is dispersion suppressor. The beam is transported. It's actually, I show it on the next slide. It's the setting of this, the second beam line, yeah? So the beam is transported through the dipoles, which are switched off, and then is focused on the patient. And in this particular case, you have two solutions for the small beam spot on the patient, 4 millimeter, and for the large beam spot of the patient of 10 millimeter. So this is one of the typical plots you have to produce in order to set up the right beam to the patient. So this is our final layout. This was already shown by Elena, the normal conducting synchrotron with the beam transfer lines. Here you see the LINAC. And we also have the same or similar design for helium synchrotron, which is much more compact. As you see, it's more or less to the scale. However, the LINAC is still quite large. What is maybe important here is that we have shielding walls. Yeah, we are producing some radiation here, and therefore we need the shielding walls. And the shielding walls have thickness of around 3 meters. And that is enough to reduce the dose to the environment to 1 millisievert per year. This is a very, very strict requirement because, I mean, there is no person who will be sitting there the whole year and taking this 1 millisievert. And we should not remember that a person working in the industry is allowed to take 20 millisieverts per year. So that those restrictions are very, very strict. And all right, this is my summary. Somehow the word summary disappeared. Basically, currently only the synchrotrons are used in the ion therapy because of the flexibility. a possibility to change easily the energy and type of the particle, and we keep the NIMMS design as based on the synchrotron. However, we have to remember that the other designs may be more exotic, which are work on in different places. For the various parts, so for the ion source, we are almost almost don't have to do any new developments. There are ion sources already now which have enough intensity for our needs. For the injector LINAC, we designed completely new injector LINAC with 3 stages, which allow to accelerate particles to different energies, and which with high duty factor allowing for radioisotope production. The synchrotron itself will be a modified PIMS design with the intensity of around 20 times higher than is done currently, and with what is very important, multi-energy extraction scheme, and with very fast extraction for flash. We also designed smaller synchrotron for helium and the superconducting machine. The high energy beam transfer lines has a very large experimental area, which is not present in current centers. It has faster beam chopper, and it will allow various dose delivery modalities, so flash and pencil beam scanning. And what is also very important, I didn't talk about it here, is the fast switching between the beam lines, because currently it takes quite some time, and we want to make it significantly faster. And finally, a very important part of the program is development of superconducting gantry, which is crucial also for the existing facilities. And that's it. I skipped a few things, but
thank you, Mariusz. Thank you, Elena. So we don't have much time for questions. So please go ahead, students. And Christoph, I guess you're taking over. Yeah. So good, thank you.
So we have a question from Celine.
Hi, thank you very much for this interesting talk. I have a question. It's a bit off topic, but you mentioned it in the beginning that your research is also taking higher ions into account up to argon. And yeah, my question is what drives this research? Because I have in my mind the fragmentation tail of carbon ion, which is already there, and yeah, the lead dependency. So why are you taking such high ions into account?
Yeah, should I answer, Elena? Or?
You want?
No, go on.
Okay, so yes, currently, okay, so heavier ions are interesting for research purposes, especially. So radiobiology, also, I mean, for space radiation as well. So different kind of research in radiobiology. But then about fragmentation, which is already present for carbon ions, there are actually some studies, again, Japanese are pioneers on that, but also at the GSI and HIT, they go in this direction. Study that aim at delivering within the tumor, delivering different ions. So an example, in the middle of the tumor, it is perhaps more efficient to deliver oxygen, which have a higher fragmentation indeed. But if you do it in the middle of the tumor, this is efficient for, I mean, if for radio resistant tumors. And then on the contour of the tumor itself, you may indeed want to deliver protons or iridium ions. So yes, heavier ions are interesting for research, but also for treatment with multi-ions.
Thank you very much.
Okay, so we have another question from Corey.
You're silent.
Can't hear you, yeah.
That's strange. Still no here.
No,
okay.
now it's good.
Can you hear me?
Yes.
Ah, cool. Thank you. I was just going to ask a question about the carbon ion production. You said they produce carbon 4+ and then strip to get carbon 6+. How is that stripping process done, and at what energy are the carbons when that happens?
All right. So the energy at which stripping is efficient starts at around 4 MeV per nucleon. Therefore, it has to be done at the end of the LINAC in principle. And how is it done? It's very simple. It's just very thin carbon foil of a few tens of micrometer thickness. They exist, and the beam just goes through, and the electrons, additional electrons are removed. But also for hydrogen or for protons, actually the dissociation of the particles takes place there.
Okay, thank you.
Question from Rita. Don't hear you if you're already.
Rita, go ahead.
Yeah.
While this is being fixed, may I ask Marius and Elena, please stay, and please can all of you put your video cameras on, because we would like to take a group photo. You know, this becomes a Zoom tradition. So while Rita is sorting this out, please turn your cameras on, all of you, if you can, and let's take a photo. Whoever's taking photos, let us know when you're done.
Oh yeah. Nice. Okay, I'm just starting, so just a minute.
Okay, please. It's important to, you know, for the record, since we can't see each other in person.
Okay, we are done with that. Thank you. So
Rita, maybe you can ask your question now. If you just unmute.
Okay, but I can read it in the chat. She's asking about the costs.
Okay.
Okay, so, well, cost is increasing with size. And therefore, for a machine for X-rays, it's about 4 million. A proton machine is about 40 millions. And the full carbon ion facility like SEEIST will cost about 200 millions, which is a big sum. That's why the consortium, that's why we want to get interest and the help also from the European Union that may see the advantage to you know, to help us to do this facility for such a large amount of countries. So, yeah. Because you talk about co-direction regarding energy. Consideration regarding energy. Okay, so yes, you're right. We care about cost, but we also care about possibility to treat patient with the carbon ions at full range. And then, okay, at the end, one has to make choices. And if, I mean, in many places now, proton facility has been installed, but still SEEIST, at least SEEIST, is meant to be both a research and a therapy facility, so a pretty big one. And that's why we want to have it all.
So if there are no other questions, I take this moment to thank Elena and Marius. Thank you so much. Really appreciate you doing this. And so I will now move over to Professor Long. That's okay. Ken, are you there? Thanks again.